Hello guys, in today's video we are going to learn how to build an LED light controller. But don't forget, this is Osem Global. If today is the first day you are seeing our video, or you've been seeing our video but you're not following our page, please follow our page, like, comment and share the video. Follow our page so that you get more updates anytime we drop a new video. Let's watch this video.
This simple circuit allows us to dim LED strip lights, and I'm going to show you how the circuit works, how to design one, and even turn it into a professional looking printed circuit. I'm going to be using these SMD 5050 LED strips, which have a relatively low current demand and provide a good level of illumination. These are wired in parallel, so we can cut them to a desired length. Just ensure you cut along the marked cut line. I'm going to use 81 LEDs split into 9 strips of 9 LEDs. To connect them, we cut some short lengths of wire and solder them, connecting the positive to positive and the negative to negative. This will give us an LED panel. When we connect this to a DC power supply with 12 volts, we see it draws a current of approximately 1.3 amps. As we reduce the voltage, the lights become dimmer and the current also reduces. We can use a switch to manually turn them on and off, but we can instead use a MOSFET, which is basically an electronic switch, to automate this and turn them on and off hundreds or even thousands of times per second by simply applying a voltage to the gate pin. I'm going to use an IRF Z44N MOSFET because it can handle the voltage and current and also has a low drain source on resistance. So we start a new project and then start adding the components in. We find the components on a supplier's website. I'm using Mouser, but you can use whoever you wish. I found the MOSFET, so we take the part number and paste this into the library loader, which is an add-on, and we click search. It finds the component, so I click add to design. I'm also going to add some terminal blocks, one for the power supply, one for a switch, and another to connect the LED strip light. We connect the power supply terminal to ground, and then the positive terminal to the switch, then the switch output to the LED terminal. Then the LED return terminal will connect to the MOSFET drain pin. The MOSFET source pin will then connect to ground. To control the MOSFET, we will use a pulse width modulation signal, and we can use a simple 555 timer to achieve this. This is an integrated circuit, which means inside it are a number of components added together to make one single component. That makes our job as a designer much easier. The component has 8 pins, which are used for different purposes. We find the component and add this to our circuit. The MOSFET will normally block the flow of current, but if we apply a voltage to the gate pin, it will allow current to flow so the LED illuminates. The higher the voltage applied, the more current is allowed to flow and the brighter the LED shines. The 555 timer will provide the voltage to the MOSFET from pin 3. This will be sent in pulses. Each pulse lasts a period of time. During this period, there will be a segment where the signal is on, so voltage is applied, and there will be a period where it is off, so no voltage is applied. The MOSFET will therefore experience the average voltage for each time period. The wider the on pulse, the higher the average voltage will be, so the more current can flow through the MOSFET and the LED will therefore shine brighter. This is pulse width modulation, because we are modulating the width of the pulse. Coming back to the 555 timer, pin 8 is the component's power supply, so we connect that to the positive track. Pin 1 is the component's ground, so we connect that to ground. Pin 4 is also connected to the power supply. This is a reset pin. If the power to this pin is interrupted, it will cause the 555 timer to reset. We don't want that for this circuit, so it is constantly powered. Pin 5 is the control voltage pin, which can be used to override the timer. We won't use that for this circuit, so we connect it to ground via a 0.1 microfarad ceramic capacitor. This prevents accidental override by filtering out noise or frequency. Pin 3 is the output, which connects to the MOSFET. Normally, only a small current flows through here. But if the MOSFET fails, it could draw a high current and destroy the 555 timer. So we will place a 1 kilo ohm resistor here to limit that and protect it. When the MOSFET is turned on, a small amount of electrons are stored inside. We need to discharge these to turn the MOSFET off. So we place a 10 kilo ohm resistor after the 1 kilo ohm and connect this to ground. This allows the MOSFET to discharge to ground. We could also use a smaller resistor, but this will work fine. Inside the 555 timer, we have 3 5 kilo ohm resistors in series between pin 8 and 1. We have around 12 volts from the power supply at pin 8, and each resistor drops 1/3 of the voltage. So here we get 8 volts, and here we get 4 volts. These will be used as a reference. Connected to the resistors are 2 comparators. The comparator has a positive and a negative input, as well as a single output. The first comparator is connected to the resistors through the negative input. The positive input is connected to pin 6, the threshold pin. Comparator 2 is connected to the resistors via the positive input. Its negative input is connected to pin 2, the trigger pin. The comparators are now connected across 2 different voltages, so it can compare them. If the positive input voltage is higher than the negative input, it outputs a high signal or a positive voltage. If the negative input voltage is equal to or higher than the positive input voltage, it will output a low voltage or low signal. We will connect pin 2 and 6 together so that the voltage is the same. The output from the comparators connect to another internal component called the flip-flop. The first comparator connects to the input called reset. The second comparator connects to the input named set. There is also an output named not Q. When the flip-flop receives a high signal from comparator 1, it outputs a high signal. When the flip-flop receives a high signal from comparator 2, it outputs a low signal. If both comparators provide a low signal, the flip-flop remains unchanged and continues. This will then pass through another component called an inverter, which simply inverts the signal it is given. If we apply a small voltage of say 3.9 volts to pins 2 and 6, comparator 1 outputs a low signal and comparator 2 outputs a high signal. This sets the timing interval to begin. The flip-flop outputs a low signal. The inverter outputs a high signal. As we increase the voltage, for example to 6 volts, comparator 1 and 2 outputs a low signal. The flip-flop remains unchanged and the timing continues. But at 8 volts, comparator 1 outputs a high signal and comparator 2 outputs a low signal. The output of the flip-flop now reverses and the output is high. This resets the timing. The output of the flip-flop remains the same until the voltage decreases to around 4 volts, where comparator 1 outputs a low signal and comparator 2 outputs a high signal. This starts the timer again. So we see that as the voltage on pins 2 and 6 increases and decreases, the output of the 555 timer changes. To control the voltage and therefore the time interval, we connect pins 2 and 6 to a capacitor. When we connect a capacitor to a power supply, it instantly reaches the battery voltage. But if we connect it via a resistor, the resistor slows down the charging time. The larger the resistor, the longer it takes to increase the stored voltage. So to charge our capacitor, we will use a fixed 1 kilo ohm resistor and a 100 kilo ohm potentiometer. The potentiometer is a variable resistor, so we can therefore vary the capacitor charging time. We will need to also discharge the capacitor in order to restart the timer. So we will add 2 diodes to create a separate charge and discharge path. The current in this part of the circuit is very small, since the resistors are in the kilo ohm range. We will use 2 1N4148 diodes, which have a forward current of around 300 milliamps, which will be fine for this application. The capacitor will be a 10 nanofarad ceramic capacitor. We will see why in just a moment. So we add these components to the circuit. Then we connect the diodes to the fixed resistor and the diodes to pins 1 and 3 of the potentiometer. Then we connect the capacitor to ground as well as to pin 2 and 6 of the 555 timer and also to pin 2 of the potentiometer. Pin 7 is the discharge pin, which is connected to our timing capacitor. Inside the 555 timer, the output of the flip-flop connects to the gate pin of an internal transistor. This controls the flow of current from the capacitor to ground. When the flip-flop output is low, the transistor is off, so the capacitor charges and the voltage begins to increase. When the voltage increases enough so that the output of the flip-flop is high, the transistor is turned on, which discharges the capacitor so the voltage reduces. When it reaches 4 volts, the capacitor begins to charge again. When it reaches 8 volts, it will then discharge. So, when charging, the current flows through the resistor, through the diode, and the left side of the potentiometer to the capacitor. The flip-flop output is low, so the discharge transistor is off. Pin 3 outputs a high signal. Once the capacitor reaches 8 volts, the flip-flop output becomes high, which turns the transistor on, and the capacitor discharges through the right side of the potentiometer and the diode. Pin 3 outputs a low signal. The transistor remains open, so the capacitor discharges until it reaches 4 volts, where the flip-flop reverses again, turning the transistor off, which starts the timing again. This cycle repeats continuously. The capacitor charges and discharges, creating a sawtooth wave, and the 555 timer outputs a square wave, which is pulse width modulated. We use a 10 nanofarad capacitor, but we don't necessarily have to. If we use these formulas to calculate the charge and discharge times with the potentiometer at 50%, we see that each cycle is around 0.69 milliseconds, which gives us a frequency of around 1.4 kHz. The human eye can detect lights flickering at low frequencies. The standard lights in your home are usually 50 or 60 Hz, and as you can see, we are operating at a much higher frequency, so we can use a larger capacitor to decrease this. But if we use, for example, a 100 microfarad capacitor, the frequency would be 0.1 Hz, and each cycle would take almost 7 seconds to complete, which would be pretty useless. So consider how it will impact your design. Okay, so I then build a simple prototype to check it all works, and it seems to be fine. I can adjust the brightness, so we will finish the PCB design. We import the components to the PCB design file and spend some time arranging these around the board. We then define the board shape and add any annotations. We generate the route to connect everything together, then we increase the track width for the higher voltage and current areas of the circuit, and also check the routes and move them if needed. Once satisfied, we create the polygon and then export our Gerber files. So now we're ready to have our circuit board printed. The boards look great. I'm really very happy with this result. So we start soldering the components to the board. I start from the center and work my way outwards. Some of the components, I flip the switch to power the circuit board on, and then I adjust the potentiometer so that the lights will increase and decrease in brightness.
This is how to build an LED light controller. Follow our page for more updates. Thank you for watching.